Our objectives in this lesson are the following. Illustrate the measures of variability. These are range, interquartile range, average deviation, variance, and standard deviation. And number 2, calculate the measures of variability for ungrouped data. I'm going to create another video lesson for calculating the measures of variability for grouped data. Let us compare and contrast. Consider the top 5 scorers of two groups in Matira Matibay Quiz B. Here are the scores of Matinik group, and here are the scores of Mat Husay group. The question is, who performed better as a group? This could be answered by our lesson for today, the measures of variability. But before that, let us recall our previous lesson, measures of central tendency, the mean, the median, and the mode. These are statistical measures that describes a typical value that is located at the middle of the data sets. Now, we will learn about measures of variability. Measures of variability are descriptive measures that indicate the degree of spread or dispersion among the values in the distribution and from the center of the dataset. Here are the different measures of variability. We have the range, the interquartile range, the average deviation, the variance, and the standard deviation. Let us start with the first one, the range, denoted by capital letter R. It is the difference between the largest and the smallest value in an observation. The formula is R is equal to HV minus LV, where R is the range, HV is the highest value, and LV is the lowest value. How do we interpret this? The higher the range, the greater the spread of values. Let us recall the scores of the two groups earlier. We have here the group Matinik. For the range, that would be R is equal to HV minus LV. Again, HV is the highest value, and here it is 35, minus LV, the lowest value, is 20. 35 minus 20 is equal to 15. So the range of Mat-Tinik group is equal to 15. Now, for the Mat-Husay group, that is again HV minus LV. The highest value for Mat-Husay is 50, and the lowest value for Mat-Husay is 10. 50 minus 10 is equal to 40. So the range for Mat-Husay group is 40. Scores of group Matinik are compressed, while scores of group Mat-Husay are dispersed. It implies that the scores of Matinik group are more homogeneous, while the scores of Mat-Husay group are more heterogeneous. If I am to conclude with respect to the range, I would say that group Matinik performed better because their scores are close to one another. The next measure of variability is the interquartile range. Again, we are talking about the ungrouped data. Interquartile range, denoted by IQR, measures the amount of dispersion present in the middle 50% of a dataset. It is the distance between the first quartile and the third quartile. For the formula, this is Q sub 3 minus Q sub 1, where Q sub 3 is the third quartile. It is the median of the data points to the right of the median in the ordered list, while Q sub 1 is the first quartile. It is the median of the data points to the left of the median in the ordered list. To give you an idea, the quartiles divides any distribution that is arranged from smallest to largest into 4 equal parts. So each part here is 25%. The 50% middlemost value is what we call the interquartile range. This is the median or the Q sub 2. This one is the Q sub 3 or third quartile, while this one is Q sub 1 or the first quartile. There are steps in finding the interquartile range. Remember the letters A, M, F, T, S. Step 1. Arrange the data values from smallest to largest. Step 2. Determine the median. Step 3. Determine the first quartile. Step 4. Determine the third quartile. And step 5, solve for the IQR by subtracting the first quartile from the third quartile. Let's have an example. Solve for the IQR of these values. Step 1, arrange the data from smallest to largest. So we have 7, and then 9, and then we have 12, and then 14, we have 15, and then we have 16, 19, and then we have 24, and we have 25. Step 2, let us determine the median. Let us count first how many values we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9. The median is the middlemost value, so that would be 15. There are 1, 2, 3, 4. 4 values to the left of the median, and 1, 2, 3, 4, also 4 values to the right of the median. Step 3, let us determine the first quartile. Since we have 1, 2, 3, 4, the middlemost value is in between 9 and 12. Next step, the third quartile. 1, 2, 3, 4, the middlemost value is in between 19 and 24. So let us solve for the first quartile. That would be 9 plus 12 divided by 2. And this will give us 10.5. For the third quartile, that would be 19 plus 24 divided by 2. And this is equal to 21.5. Last step, let us solve for the interquartile range, and that is Q sub 3 minus Q sub 1. 21.5 minus 10.5. And this will give us 11. So IQR of these data values is equal to 11. Let us have another example. I just added 30 in the list. So step 1 again, we're going to arrange from smallest to largest data. We have already arranged this a while ago. Let me just add the last value, which is 30. Let us count the number of values. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This time, we have an even number, 10. So the median is the middlemost value, and that would be in between 15 and 16. For the first quartile, since we have 1, 2, 3, 4, 5, the middlemost value of 5 values is 12. For the third quartile, we have 1, 2, 3, 4, 5. So the value is 24. Let us solve for the first quartile. We already have it. That is 12. Third quartile, we already have it. That is 24. And last step, solve for the IQR. That would be Q sub 3 minus Q sub 1. That is 24 minus 12. And this will give us IQR, which is equal to 12. The next measure of variability is the average deviation, denoted by AD. It measures the average value by which any value in a distribution deviates from the mean of a dataset. For the average deviation of the sample, we have the summation of the absolute value of x minus x bar all over n. For the population, we have the summation of the absolute value of x minus mu divided by capital N, where again AD is the average deviation, x here is the individual score, X bar and mu is for the mean of the sample and population respectively. Small letter n and capital N is the total number of values for the sample and the population respectively. Let's have an example. Let us recall the formula. AD is equal to the summation of the absolute value of x minus x bar all over n. We are going to need a table for this. So let us enumerate our x values. These are 35, 31, 28, 26, and 20. For the x bar, we're just going to add all of our x values and then divided by 5 because we have 1, 2, 3, 4, 5. 5 values. 35 plus 31 is 66. 66 plus 28 is 94. 94 plus 26 is 120. 120 plus 20 is 140. So 140 divided by 5. And this will give us 28. So this is our x bar, 28. Now for the absolute value of x minus x bar. The absolute value of 35 minus 28 is absolute value of 7, and that is equal to 7. Next one, the absolute value of 31 minus 28, and that is equal to absolute value of 3, which is 3. Next one, the absolute value of 28 minus 28 is the absolute value of 0, of course, 0. Next, the absolute value of 26 minus 28 is the absolute value of negative 2, and that is positive 2. Last one, the absolute value of 20 minus 28, that is the absolute value of negative 8, and that is positive 8. Now, let us get the sum of this. 7 plus 3 is 10, plus 0 is still 10, plus 2 is 12, plus 8 is 20. So, the summation of the absolute value of x minus x bar is equal to 20. We are going to use this value and substitute it here in our numerator. And for our n, again, that is equal to 5. So we have 20 divided by 5, and this is equal to 4. So how do we interpret this? On the average, the scores are 4 units from the mean. The next measure of variability is the variance. Variance is the average of the squared differences from the mean. It measures the dispersion of a data set. It indicates on average how far is each value in a data set is spread out. Again, we have two formulas. For the sample variance, we have the summation of the square of the difference of x minus x bar all over n minus 1. Or in simpler form, this is the summation of the square of the deviation divided by the n minus 1. For the population variance, we have sigma squared is equal to the summation of the square of x minus mu all over capital N, where S squared and sigma squared is the variance, x again is the individual score, x bar and mu is the mean of the sample and the population respectively, and n and capital N is the total number of values for the sample and the population respectively. How do we interpret variance? High variance means that data points are more spread out from the mean and from each other. Ever wonder why do we have to square this? Variance measures the dispersion of a set of data points around the mean. Because dispersion is about distance, and we know that there is no negative distance, hence dispersion must be a non-negative number. That is why we square to obtain positive results. Now, take a look at the denominator. You might ask why in sample we have n minus 1, while in population we only have n. When you have a population data, you can get an exact value for the variance. But when you use sample data, your sample standard deviation is always used as an estimate of the population standard deviation. N minus 1 here means a smaller denominator, and it will yield to a higher variance compared to just dividing by n. This accounts the higher potential variability because we are just dealing with samples. It is better to overestimate rather than underestimate variability in samples. When we are dealing with population, we know all the data and we can exactly calculate for the variance. With samples, there is a higher possibility of variability, and the n minus 1 accounts for it. Let's have the example. In the beginning, I have mentioned that these are the scores of top 5 scorers, meaning this is not the totality of the scores, just a sample. So we're going to use the formula for the sample variance, and that is, again, S squared is equal to the summation of the square of the difference of x minus x bar all over n minus 1. Again, we're going to need a table for this one. We already enumerated our x values, and we have also computed for the value of our x bar. Now, for x minus x bar, or the deviation, 35 minus 28 is equal to 7. And then we're just going to square this value. 7 squared is equal to 49. 31 minus 28 is equal to 3. 3 squared is 9. 28 minus 28 is equal to 0, and the square of 0 is still 0. 26 minus 28 is equal to negative 2. Negative 2 squared is equal to positive 4. 20 minus 28 is negative 8, and negative 8 squared is positive 64. Now, let us get the sum of the deviation. We have 7 plus 3 is 10, plus 0 is still 10, plus negative 2 is positive 8, plus negative 8 is equal to 0. Take note of it. The sum of the deviation of the values from the mean is always equal to 0. Now, let us get the sum of the square of the deviation. 49 plus 9 is 58. 58 plus 0 is still 58. 58 plus 4 is equal to 62. 62 plus 64 is equal to 126. We're going to substitute this value in our numerator. And again, our n is equal to 1, 2, 3, 4, 5. So 5 minus 1 for the denominator. 126 divided by 5 minus 1. 126 divided by 4. And this will give us 31.5. The last measure of variability, which is very much related to the variance, is the standard deviation. It is the square root of the variance. It measures on average how far each value in a data set is from the mean. It is considered the most important measure of variability. For the sample, the standard deviation formula is the square root of the sample variance. And for the population, the standard deviation is the square root of the population variance, where S and sigma is the standard deviation, X is the individual value, the X bar and mu is the mean of the sample and population respectively, and the small letter and capital N is the total number of values for the sample and the population respectively. Now, how do we interpret the standard deviation? High standard deviation means that data points are more spread out from the mean. Let's have the example. So again, the formula is the square root of the summation of the square of the difference of x minus x bar all over n minus 1. And this portion here, the one inside the square root, is the formula of the variance. And we have computed its value earlier, and that is 31.5. To solve for the standard deviation, we just have to get the square root. So the square root here and this exponent 2 here will cancel out. The square root of 31.5 is 5.61. Recall that our mean is equal to 28. So this means that the scores are clustered within 5.61 around the mean. That is between 22.39 and 33.61. How did we get these values? 28 minus 5.61 is 22.39. And 28 plus 5.61 is 33.61. The standard deviation gives us the idea of what is standard. Hence, we will know which is normal, extremely small, and extremely large value in a data set. Earlier, we solved for the average deviation and it is equal to 4. Take note that the standard deviation is always greater than the average deviation. For the summary, here are the things that we discussed in this lesson. Take time to understand this. Now, it is time to check your understanding. Pause this video for more time. Let us answer. We're going to solve for the interquartile range, average deviation, variance, and standard deviation. This time of the Math-Husay group. We are not going to solve anymore for the range because we already computed for that earlier. So let us start with the interquartile range. So first step, we have to arrange these values in ascending order. So we have 10, 20, 24, 36, and 50. Step 2, we have to look for the median, the middlemost value. Since we have 1, 2, 3, 4, 5, this is odd number. The middlemost value is the third one, so that is 24. Now, let us solve or determine the first quartile. We only have two values here, so the first quartile is in between 10 and 20. And the third quartile is in between 36 and 50. The first quartile is 10 plus 20 divided by 2, and that is equal to 15. The third quartile is 36 plus 50 divided by 2, and that is equal to 43. To solve for the interquartile range, you're just going to subtract quartile 1 from quartile 3. So we have 43 minus 15, and that will give us 28. Letter B, let us solve for the average deviation. The formula again is the summation of the absolute value of x minus x bar all over n. We're going to need a table for this. These are our x values, 50, 36, 24, 20, and 10. To solve for x bar, we're just going to add all these values and then divided by 1, 2, 3, 4, 5. So our n is equal to 5. 50 plus 36 plus 24 plus 20 plus 10 is 140. So we have 140 divided by 5. And this is equal to 28. This will be our x bar. For the absolute value of x minus x bar, first we have 50 minus 28, the absolute value of 22, which is also 22. Then we have 36 minus 28, absolute value of it is 8. 24 minus 28, negative 4, the absolute value of that is 4. 20 minus 28 is negative 8, the absolute value of that is positive 8. 10 minus 28 is negative 18. Absolute value of that is positive 18. Now let us compute for the sum. 22 plus 8 is 30. 30 plus 4 is 34. 34 plus 8 is 42. And 42 plus 18 is equal to 60. Let us substitute this value in our numerator divided by our n, which is equal to 5. And 60 divided by 5 is equal to 12. Next one is the variance. The variance, since these are just the top 5 scorers, we are going to use the formula for sample variance. Again, we're going to need a table for this one. We already enumerated our x values. We have computed a while ago our x bar. Now for the deviation. 50 minus 28 is 22. Square this, and this is 484. 36 minus 28 is positive 8. Square of that is 64. 24 minus 28 is negative 4. Squaring this is positive 16. 20 minus 28 is negative 8. Square of this is positive 64. 10 minus 28 is negative 18. The square of this one is positive 324. To check, let us get the sum of this. It should be equal to 0. 22 plus 8 is 30. 30 plus negative 4 is positive 26. Positive 26 plus negative 8 is positive 18. And positive 18 plus negative 18 is equal to 0. Take note that the sum of the deviation from the mean should be always equal to 0. Now let us get the sum of the square of the deviation. 484 plus 64 plus 16 plus 64 plus 324 is equal to 952. Let us substitute this value in our numerator, and then our n is 5, so we have 5 minus 1 for our denominator. So 952 divided by 4, and this will give us 238. Last one is the standard deviation. And once again, this is just the square root of the variance. We have computed for the variance a while ago, and it is equal to 238. Let us get the square root of this. This will be cancelled out, and the square root of 238 is 15.43. I have tabulated the results from the two groups. Looking at the difference, the results of different measures of variability from the Math-Husay group are way greater than the Math-Tinig group. This means the scores in the Math-Husay group are more dispersed. If I were to give my answer to the question, who performed better as a group, I would say that it is the Math-Tinig group, because their scores are close to one another. Also, the average distance of each score from the mean is smaller than that of the Math-Husay group. Gets? Our next lesson is measures of variability for grouped data.